Hello, and welcome to the channel, everyone! In this video, we'll be exploring surds, those special irrational numbers expressed in radical form, such as square roots and cube roots. Now, what exactly are irrational numbers? These are numbers that cannot be written as fractions, meaning they go on forever without repeating. Surds help us represent these numbers neatly using the radical symbol. Let's take a simple example. The number 4. If we apply different roots to it, we get some interesting results. The first root simply gives us 4. The second root, or square root, gives us 2. The cube root results in a recurring decimal of 1.587. The fourth root gives us a recurring decimal of 1.414. Notice that while 4 and 2 are rational numbers, the last two results, 1.587 and 1.414, are irrational. They continue infinitely without forming a repeating pattern and cannot be written as fractions. Now, let's define a surd properly. A surd is an irrational number that involves an nth root. Since these numbers cannot be expressed as fractions, using the radical symbol allows us to represent them without writing out their endless decimal forms. Because 4 and 2 are rational, they are not considered surds. However, expressions like the square root of 2 or the cube root of 5 are surds. The order of the root doesn't affect whether a number is a surd, nor do mathematical operations like addition or multiplication. Let's also recall the law of indices when dealing with fractional exponents. Any term with a fractional exponent can be rewritten in radical form and vice versa. This law tells us that if we have a base a raised to the power of m over n, it can be rewritten as the nth root of a raised to the power m. For example, cube root of 4 is the same as 4 raised to the power of 1 over 3. The fourth root of 4 is 4 raised to the power of 1 over 4. Before we dive into solving equations with surds, let's go over some important laws. From this point onward, we'll use the radical symbol to represent square roots without explicitly writing the 2. For any real and positive values of a and b, here are 3 key laws of surds. Multiplication rule: the product of two radicals can be combined under a single radical. In other words, the square root of a times the square root of b equals the square root of a times b. Division rule: the division of two radicals follows a similar pattern. The square root of a divided by the square root of b is the same as the square root of a over b. Elimination rule: multiplying a square root by itself cancels the radical. This connects to the product rule of indices. Before we continue, let's address some common misconceptions. Notice that in all 3 laws of surds, there is no addition or subtraction involved. That's because these operations do not follow the same rules as multiplication and division. This means that the square root of a plus the square root of b is not the same as the square root of a plus b. The same applies to subtraction. Now, let's look at some examples of simplifying surds. Feel free to pause the video and take a moment to try these questions on your own. All right, I hope you had a chance to attempt them. As a general rule, when simplifying surds, always look for square numbers within the radical and factor them out. For example, in part A, the number 12 contains the square number 4. Using the first law of surds, we can rewrite this as the square root of 4 times the square root of 3. Since the square root of 4 is 2 and the square root of 3 remains a surd, we stop here. The final answer is 2 square root 3. In part B, recall that surds cannot be added or subtracted directly. Instead, we break down each surd term by factoring out square numbers. Remember, square numbers include 1, 4, 9, 16, 25, and so on. For 80, we rewrite it as 16 times 5, since 16 is a square. For 45, we write it as 9 times 5, since 9 is a square. Now, we evaluate the square roots. The square root of 16 is 4. The square root of 9 is 3. This gives us 4 square root 5 minus 3 square root 5, which simplifies to square root 5. In part C, we perform expansion. The second term, 2 square root 5 times square root 5, simplifies to 2 times 5, because the third law of surds tells us that multiplying a square root by itself cancels the radical. The first and fourth terms both contain square root 5. so we can combine them into 5 square root 5. The non-surd terms are 2 times 5 and minus 3, which results in 7. Thus, the final answer is 5 square root 5 plus 7. The most important strategy when simplifying surds is to identify the largest square factor inside the radical and factor it out. If you can't spot a large square immediately, start with smaller ones like 4, 9, or 16, and repeat the process until no more square factors remain inside the radical. Now, let's move on to conjugate surds. For any rational numbers p, q, and a, where a is positive, the expressions p plus q square root a and p minus q square root a are conjugates of each other. Together, they are called a pair of conjugate surds. So, how does this help us solve equations involving surds? Well, the product of conjugate surds is always a rational number. This is a powerful property that we can use to simplify and solve expressions involving surds. Let's verify this by performing multiplication and expansion. The product we obtained here is a rational number because the radical terms have been eliminated. Since the original values were rational, the final result remains rational as well. We don't actually need to expand each term individually. Instead, we can use a useful algebraic identity that helps simplify expressions involving conjugates. The process we just applied is called rationalizing, where we multiply by the conjugate surd to eliminate radical terms. This technique is particularly useful when dealing with fractions that have radicals in the denominator. Let's illustrate this with some examples. Feel free to pause the video and try them out. All right, for the first example, we multiply the denominator by its conjugate. Since we are essentially multiplying by 1, the value of the fraction does not change. In the denominator, the radical terms cancel out, leaving us with a rational number. We then simplify the numerator accordingly, resulting in the final expression. The second example, we use the same technique by multiplying the fraction by the conjugate of the denominator. Instead of expanding everything step by step, we apply a known algebraic identity to simplify the expression efficiently. After simplifying both the numerator and denominator, we arrive at the final answer. In both cases, the final result no longer contains radical terms in the denominator. This confirms that we have successfully rationalized the fraction. Always remember, your final answer should never have a radical in the denominator. Another common type of problem involves solving equations that contain surds. To eliminate the radical, we can square both sides of the equation. However, before doing so, we first isolate one of the surd terms so that each side of the equation contains only one surd. Once the surd is isolated, squaring both sides removes the radical, transforming the equation into a simpler form that we can solve directly. At this point, we solve for the unknown value. However, be careful. Squaring can introduce extra solutions that may not be valid. To confirm the correct answer, we substitute the solution back into the original equation and check whether it holds true. Finally, surds can also appear in real life scenarios where equations involving radicals need to be solved to find meaningful values. Feel free to pause the video and try this problem on your own. This question gives us a cylinder with a circular base and a volume of 6 plus 2 root 3 pi cubic centimeters. The radius of the cylinder is 1 plus root 3 centimeters. Our task is to find its height. To solve this, we recall the formula for the volume of a cylinder, which is base area times height. This means we need to express the volume in terms of the given radius and solve for the height. Substituting the given values into the formula, we rearrange the equation to make height the subject. This results in a fraction that contains surds in both the numerator and denominator. However, the denominator cannot contain a surd, so we need to rationalize it. How do we do that? We multiply both the numerator and denominator by the conjugate of the denominator, which in this case is 2 minus root 3. Using an algebraic identity, we simplify the denominator, reducing it to a rational number. Expanding and simplifying the numerator, we ultimately find that the height is 3 minus root 3 centimeters. From this, we can see that the first value is 3, and the second value is -1. Now, let's look at some real-life applications of surds and radicals. These concepts appear frequently in mathematics, particularly in geometry. Surds are useful for calculating lengths and distances. For example, they play a key role in Pythagoras' theorem, which helps us determine the length of the hypotenuse in right-angled triangles. In coordinate geometry, radicals help us find the distance between 2 points by substituting their x and y coordinates into the distance formula. Beyond mathematics, radicals also appear in physics and engineering. They are used to calculate the period of a pendulum, where we substitute the values for length and gravitational force into a radical expression. In hydraulics, radicals help determine the velocity of water flowing from a pipe, aiding in the design of efficient piping systems. In summary, radicals and surds are incredibly useful in mathematical calculations and real-world applications. They play a significant role in various fields, often without us even realizing. That's all for now. I hope you gained some valuable insights from this video. Thank you for watching until the end. Feel free to share your thoughts in the comments. And remember to stay curious, keep learning, and I'll see you in the next one.